licenses, the 06 or the 07. Okay, so here's how it works. If you've taken the course within that period and you've received credit for it, you do not receive credit again. And I'm not the one that determines that. L&I determines that. So we've had a couple instances where people have taken it and they're submitting for credit, but once you take it within that 3-year period and apply. Before, I'm the local representative for Belimo. Been doing this for about 10 years now, so that's probably a feat in and of itself, probably the longest I've worked anywhere else. I'm the chief cook and bottle washer. Some of you guys have been on site with me, maybe not, but I live in Camino Island, and I'm local here. I've been in this industry for 30-some years, probably most of it in the Seattle area. Worked as a consulting engineer in a couple of firms downtown. Started out wearing a tool belt, industrial process control, for 5 years after getting out of the Navy, and spent about 5 years working for Puget Power in energy conservation. So I've sort of been involved with controls most of my career. So this is probably my last paid gig, and in a couple of years, hopefully I'll be selling it again. But in the meantime, what we're going to do for the next 2 days is we're going to go through Belimo 101. And some of you guys know what I'm talking about. This is like our introductory level course to dampers, air control dampers, and valves. Okay. So today we're going to go through the air side. We're going to do the actuator side. And then on Thursday, whatever we don't finish today at 8 o'clock, we'll finish up on Thursday. Just make sure that, as far as the L&I stuff goes, you must attend both courses in order to get credit. You can't, it has to be that way no matter how long it lasts, right? So typically, even though you get credit for 8 hours, we typically wrap up less than that, but my point is you have to be here for both. So you have to sign in both times, and that's pretty tough. All right, so let's get going. You guys who've been here before know this drill, but what you guys should have is this way oversized binder with a catalog inside of it, and I think what you've got here is you've got the 2016 catalog. That'll be good for our purposes now. Just for you guys, for your information, and Tom can help you with this. In another month, we go to our new catalog, which will have some new products in it and things like that. If you want a new catalog, you can talk to Tom, and they'll be able to set you up. But for right now, we're going to work with the 2016 catalog. You guys got all the swag, right? Did you get the wrenches and the screwdriver and the highlighter and the 4-color pen? Yeah, it's all right. So you got all that. The way that this course works the best is that I sort of keep rolling, and if you have a question, I like you to answer. Just when it comes up, just ask it. Okay, so if I can answer it quickly, I will. If I can't answer it quickly, then we'll take it offline, and I'll get you the answer eventually. But I'm not going to ask for questions. So just ask the questions as they come up, and we'll just keep rolling that way. Okay, I'm going to try to break at least a couple minutes on the hour so we can get up and go to the bathroom and just take a stretch so everybody stays awake. I know you guys have had a full day, as I have too. But I get to stay awake as I talk now, right? So we can't get on that. I think that's pretty much it. I'm gonna say to you now that for those of you taking the course before, we changed the format a little bit. So I'm gonna say that workbook that's in this binder, which I forgot to mention, right? There's a workbook in this binder. It's loose leaf. I would recommend that if you've taken this course for the first time, that you stick on that workbook and make sure, because what happens is we're going to go through a damper sizing calculation, and we're going to be flipping back between these slides. And so if you're not familiar with what I'm doing, then stand next to the workbook. It's going to help you. Okay. Just going to give you that word of advice. All right. So what we're going to do. This is what we're going to do today for the next couple hours. We're going to talk about the nomenclature, right? The catalog. We're going to go through the Belimo nomenclature. If you guys, how many guys are familiar with Belimo in general? The guys that have been around for a while. You guys pretty familiar? Okay. So we got funny letters in our model numbers. We sometimes you don't always know what they mean. We're going to try to decipher that a little bit today, as far as that goes. We're going to go through the process of sizing a damper actuator. How many people ever sized a damper actuator for a damper installation? Nobody's ever done it? You normally wouldn't do it, right? Because you guys are, everybody here service? Mechanical service?
Or install, special projects, install, yeah.
You have install, service, No engineering?
I think there's some electricians in here, right?
Yep.
Yeah,
Okay.
oh, yeah.
All right. Well, yes, you guys are normally don't get involved in that. However, I'll tell you the feedback on these courses, when people say what you liked about it, and you're going to actually there is an evaluation sheet in that front pocket that I'm going to ask you to fill out on Thursday. But one of the feedback on this course is people like to know how to size a damper actuator. And the reason I think is, particularly on the service side, if you're going up and you're looking at a failed damper actuator, you say, well, okay, it's failed, I just replace it with whatever it's there, right? The sort of the level 2 troubleshooting is, well, why did it fail, right? Is it over torqued? I mean, did it burn out? What happened, right? So I can tell you from personal experience, over the last 10 years, I've had 3 instances where I go into a customer's facility, maybe with MI control. I think every time it has been with MI. Go in on a joint call, we talk about something, and then the guy says, well, I got this air handler where I got this situation where under certain circumstances the damper seems to stick and it won't drive properly. And every single time I've gone in there, it's been where the actuators have been undersized. That is to say, there probably should have been 2 actuators on that damper, and there was only 1. So you guys can see there where it makes sense, right? Under certain conditions, that torque is not enough to drive that damper. So this damper size, even though it sounds a little bit egghead, by egghead I mean engineering stuff, it's stuff that might be useful for you. Good news is, once we go through this, if you want to do this kind of sizing calculation, we have a retrofit app that you have on your phone. I think there's a Droid and an iPhone app. You can just do it on your phone. So we're just going to do it the hard way the first time. I'll show you how to do it. We're going to talk about, I actually have a bunch of samples out in the car. We'll go through some, we'll look at some of the damper actuators that we have, let you pass around, let you look at them. We're going to go through mounting and wiring of spring return and non-spring return actuators. This is the lab, right, where we haul out all that PS100, put you guys in, I don't know, there's going to be groups of 3 here because we only have I think we have 8 or 10 setups, so we'll have to probably collaborate on that. We'll go through, particularly for the guys that, well, maybe I should ask a question. In terms of the field, what's the shortest period of time that somebody's been in the business?
3 days.
Who's the rookie? 3 days? All right.
A year.
3 days, man. 3 days.
A year.
3 days.
Well, shit, it's a year and a half.
No, that was a year and a half. All right. 360 days. That's
3
right.
days.
Anyway, well, my experience with McDonald Miller is people stay here a long time, right? So we have a lot of
How do you stay so long?
I don't know. All right. So, but for the guys that haven't done it before, we're going to wire them up, and we're gonna talk about this thing called normal and fail. So you guys have taken the course before, you know what I'm talking about, right? The difference between a normal setup and a fail setup. This is something that is mystifying to a lot of people in our industry. They don't understand the difference, and they confuse the two. So we're going to hopefully clear that up for anybody where that's an issue now, and we'll do that. And then if we have time, we'll talk about the zip economizer. I'm not sure if we're going to have time for that. This is actually our comparable or competitor to the Jade, which you guys are probably well aware of. And we actually have come out with a new, just as an aside, we've come out with a new version of the zip called Zip 2.0, which actually it's a BACnet compatible device. So it's actually able to be integrated into an existing BACnet system, and you can actually look at the data that's on it. We'll see how that goes. All right, so let's go. So, Belimo. It's probably never spent nights thinking about this, but this Belimo is not a disease like bulimia or anything like that. It's actually an acronym for 3 Swiss words. In 1975, 3 Swiss engineers came up with this idea of a direct coupled actuator. Does everybody know what I mean by direct coupled? What do I mean by direct coupled? You put the thing right on the shaft, right on the drive shaft. You can connect this thing right onto the drive shaft. That was a big deal back in 1975. It was a big deal. The other thing that was a big deal was it was electronic. I started my career in 1979 in a private sector, and I remember hearing about these spring return electronic actuators. And I said, "Yeah, right. I'm not using any of those, right?" Because I was an industrial. Well, here I am, right? 30 years later, working for the people who invented them. So direct coupled electronic actuator is a big deal. So these guys came up with this name based on 3 Swiss words. So the first word is beraten. This has to do with consulting. So the idea is that we consult with our customers on solutions to, at the time, actuator problems. But some of you guys have been involved, we've been working on valve problems, right? So now we have valves and actuators. The second word is liefern, has to do with delivery. That's about delivering on time and accurately, all that kind of stuff. And then the MO is for mantra, and that has to do with this direct coupled concept, right? That you can directly couple right to the damper shaft. Question for the guys that haven't taken the course: if you don't direct couple, what are your options?
Gears.
All right, gearing so much. Mostly crank arms and push rods and ball joints and all that sort of stuff that you see in the. Well, we still have it, right? There's still places where we cannot direct couple. And I'll actually show you a solution that we have, which is sort of in between, where you can direct couple, but you need some hardware to do that. So there's the old guy right there. That's the original first generation spring turn. It's not quite actual size. It's probably a little bit bigger, but you can still see the clamp, the old shaft clamp you have, and obviously the spring is external. But that's the first 1975 vintage. Probably weighed about 15 pounds, I would guess, or at least 10. All right. So if you guys want to follow in your workbook, actually I'll steal. Do we have an extra one here, or are we all out? No. I mean, I just want to.
That was for you.
Yeah, I was just going to use this as a reference point. That's it. Is it? Okay. All right. So if you're following along in the workbook, I'm going to start off on page 5 or page 6. So this question of why do we need energy management systems, I'm not going to spend a lot of time on this, but I'm just going to briefly touch on this because it's something that, particularly for the guys that are starting out their careers, there's a couple of things here that I think are important, so I'm just going to touch on those. Occupant comfort and safety, that's becoming more and more of a deal. Now comfort, how many people deal with like customers directly? Like, where you got hot calls, cold calls, that kind of stuff, right? You can't please all the people all the time, right? Although you can define comfort, ASHRAE actually defines it. But safety is another deal. So when I say safety, what am I talking about in terms of HVAC?
Fire life.
Life safety, which would be fire, smoke damper actuators, that's correct. But what's another safety issue? Carbon dioxide, right? Ventilation. That's becoming more and more of a big deal, right? It's becoming a big deal as far as do you have proper ventilation? Can you prove that you do? Things like that. So that's one thing as far as energy management systems. We can actually now, you guys know what I mean by demand controlled ventilation?
Yeah.
Does everybody know what I mean? Does everybody know what I mean by that?
CO2 based.
Right. You basically measure the carbon dioxide in the room and extrapolate that to the number of people in the room. And if there's nobody in the room, you can bring your ventilation down theoretically to 0, right? If there's no equipment in there. And that's a good deal, right? Energy saving type thing. Anyway, the energy management systems allow us to be able to monitor airflow and things like that and make sure we have proper ventilation. The productivity thing, even though we poo-poo this, for the people that own these buildings and that rent these buildings, it's a big deal. So all of your salaries and all of my salary and all the equipment costs sort of pales in comparison. If people are uncomfortable, they don't produce work. They don't produce, and it's a real thing. So obviously, if you're caught in a position of saying, well, it's too hot, it's too cold, or I don't have enough ventilation, the energy management systems can actually help you with proving that. 3 and 4, this thing here, energy efficiency and data acquisition sort of go hand in hand, in my opinion. That's my car should be all the way down because the voice recognition is not working anymore. So anyway, but this whole data acquisition thing, we take a lot of data, right? But what the hell do you do with it, right? There's people that take data, but they don't do anything with it. So I think in the future, these two are going to become more important. Energy efficiency obviously is important, but what's going on around here is what do you think the issue is with energy efficiency around here? We don't pay a lot of money for energy, right? We only pay 8 cents a kilowatt hour. Down in San Diego, they're paying 20 cents a kilowatt hour plus time of day. You can pay up to 35 cents a kilowatt hour for electricity down in Southern California. So I think for the guys that are younger in your careers, I would be more informed on this energy efficiency thing, because you guys are the people that the people are going to be looking to. It's like, how do I make my building more efficient, and how do I get the data I need to do that? Equipment life and maintenance are things that sometimes I guess we take for granted now that we can actually look at. For instance, if things are short cycling, we know everybody knows what short cycling means, right? So short cycling of equipment we can use with energy management systems. We can see if it's short cycling. We can do, does anybody, you guys do predictive maintenance? Does anybody know what I mean by that? So you look at it, and you know when you need to actually lubricate bearings,
Yeah,
or
rather than time-based maintenance. So we're getting into that more with ultrasonic and vibration. And
right. So you can look at bearing temperature, you can look at all kinds of things and say, yeah, I need to do something with this piece of equipment. That's what our energy management systems afford us. Now, like I said, it become more and more common over the years, but this is sort of what we think are probably some of the more important points about why we have them. So control system sequence, I hate this slide. So what I'm going to do is I'm just going to draw you my bonehead description of a control loop. It's sort of a diagramming thing. So I'm going to start out with the controller. So that controller is a black box. Now, because I came from process control, I don't really care what the process is. This thing could be like temperature control on a space. It could be flow control on a flow control loop. It could be raising and lowering window shades. I don't really care. But what I do know is that whatever process that we have, I need to sense some value, right? Some parameter, right? We call that the measured variable. And that measured variable, whatever it is, it could be temperature, it could be pressure, it could be pH, whatever. It goes into the controller in a value that it can understand, right? It could be an analog signal, 4 to 20. It could be 2 to 10 volts, whatever it is. We call this, I don't know, you call it the process variable. It's known by a number of different names. So what's the other input to the controller?
what it's supposed to be.
Right, the set point. So the set point comes from everything. So inside the controller, there's actually a couple processes that occur. The one thing is, we call it error summation. So what happens is, the controller looks at the set point, and it looks at the value of the measured variable, the process variable. It comes up with an error signal. Then it goes into this thing called, how about PID? So these are the settings within the controller that basically establish how it responds, right? Are you guys familiar with what I'm talking about here? So you have different values of proportional and integral and derivative. Well, in HVAC, we don't use D so much. We use proportional and integral. And then most of our loops are accommodated by those two responses. All right, so back to the loop. The controller does all the magic in here. And then what it does, it outputs what I call a command signal. So that command signal, it could be in the form of a two-position signal, like a relay closure. It could be a 2 to 10 volt signal or some sort of analog signal. It puts it onto an actuator. This actuator is on what we call a final control element. And that final control element could be a damper, like an actual damper, or it could be a valve. Okay? So this is a loop, right? So how does it loop back?
It looks for a change in the sensor.
Right. So the feedback is through the process, right? The feedback, what we call, this loop in general is what we call a negative feedback loop. It actually has to do with the sign of the set point. And so the set point is actually a positive value. The feedback is what we call the process variable is a negative value, and that's what we call a negative feedback loop. But yeah, the actual loop itself is this. Now we have one more signal, which we'll talk about today, where from the actuator to the controller, or to the head end, whatever it is, this is called position feedback. Well, in most cases, it's called position feedback. We actually have valves that will feed back on flow. We can actually get a flow output. But in general, the command signal is, I told you to do this, right? I told you to go here, like say for position. The actuator says, well, here's where I really am. So I don't know if you guys have these systems, but on data centers, anybody work on data centers at all? Okay. So in data centers, the typical criteria for data centers, unlike outside air, return air, things like that. The difference between this and this, something like that, 5%. So they want to know exactly where those outside air dampers are. They want to know exactly where they are. And so that's where feedback becomes important. On office buildings, not so much, right? I mean, we don't normally use feedback, but it's available on what we call proportional actuators, and we'll talk about that in a minute.
So it's something for like the newer guys, like 3 days guy here. What he's showing there with that C, that would be like your Honeywell Spider controller,
right?
Or your Johnson Controls FX Explorer, or Allerton Tux card, or any number of those field controllers that's mounted on a heat pump or mounted on a VAV box,
Right.
where it's actuating the primary air damper, and it's reading airflow coming through that damper, and based on that airflow and the set point, it makes a decision on how much, where it's going. So that's a perfect example of your field level of your control system.
Yep. Now, as far as these integrated systems, I don't spend a lot of time on this. Does anybody know if they work in an integrated building? Like to say that, now what I mean by integrated building is, what I mean is that all of the major systems of the building, so we talk here, we've cut this down, say life safety, energy management, and HVAC, they're all on a single backbone. By that, what I mean is like a protocol, a communication protocol. Everybody have like where even the elevators are on back there, or something like that? Or lawn, right. Do you have a building like that?
I think of a few.
Most of the time, you've got different ones, right? Like the elevator has its own deal, and the HVAC has its own deal. Sometimes the lighting and the HVAC are put together. I would tell you that for the most cases, this isn't very common, but here I'm gonna spring this thing on you. This is a new thing. I'm just gonna see how many people have heard of this term before. Has anybody heard of a thing called Internet of Things? How many people have heard of that term? Okay, not very many. It's coming, but what it is there, that's a real like crazy sort of idea at this point, where now you're going to have this thing out in the cloud that's going to sort of control the stuff in your buildings. It's not real popular, as you might expect, with our industry right now, but things are happening.
Even like chemical pumps for condenser water loops and everything. Current sensors on your pumps, and it's just sensors throughout everything.
Yeah, well, we'll see how it goes. Right now, it's a new thing, but it's sort of a little bit disconcerting to those of us that have worked on hardwired stuff all our lives. It's a little bit different. All right, so let's get back to. We'll get back to some of the more practical things here now. So hey guys. All right, so when we talk about points. When control guys talk about controls, they talk about 4 different types of points. So they talk about analog inputs, analog outputs, digital inputs, and digital outputs. Sometimes they're called binary inputs and binary outputs, but it's the same thing, right? Because does everybody understand the difference between analog and binary? Anybody not understand that? It's important. Speak now. Okay. So analog inputs. And you actually have a list of them in your workbook on page 7. You have anything that has like a varying signal, right? So you have a temperature, you can have a temperature sensor, a humidity sensor, a flow sensor, a power meter, something like that. It's an analog signal. It varies across a given range. 2 to 10 volts, 4 to 20 milliamps, 0 to 5 volts, something like that. So the signal goes across that range, and it has a value of that voltage for every single temperature or position it can take. So that's an analog input. Now, inputs and outputs are referenced to the controller, right? That's the input to the controller and the output to the controller. So an analog input very well it could be this, right? This sensor going in the controller is an analog input. What's the other analog input? Could potentially an analog input here. The feedback, that's right. The feedback is also an input to the controller. Analog outputs are actually on digital inputs. This would be like most common, like a freeze stat, right, on an air handler. That's in a digital input. Current sensing relays, flow switches, proof switches, things like that. It's just a contact closure that says something has happened. I have flow, I have fire, something like that. I'm freezing, something like that. Right. The analog outputs are going to be any analog output from the controller. That would be that command signal that I referred to over there. It could be 4 to 20 milliamps. It could be 0 to 5 volts. Even you guys are probably aware Honeywell makes there's an older Honeywell Series 90 controller. Its output is 0 to 135 ohms. A little bit weird, right? But that is its command output. It actually outputs resistance instead of voltage. And then finally, digital outputs is just going to be like a start-stop relay or something like that. It says, okay, I want you to do something. Either I want you to do something, or it could be an alarm. It could be an alarm saying something has reached a certain level, and you need to know about it. So all of the controls that you guys deal with out in the field are going to have one of these 4 signals. So they refer to, if you talk to a control guy, you can say it's an AO or an AI or a BI or a BO. That's the abbreviations in the field. All right. So now there's a little bit of a test here. Now those you guys have taken the course before probably know the answer to this, or hopefully you do. So if you're looking at these 2 model numbers for Belimo, which one is the spring return model? So how many for 1? Only the new people that take it. Nobody for 1? How many for 2? Okay, a bunch of hands for 2? Okay. So why did you think it was 2?
Yeah,
the SR. I say, yeah, it's spring return, man. That's easy. Why the hell is he even asking the question? And you would be wrong, right? So you're wrong because, and this is sort of the point of it, SR does not mean spring return in Belimo language. You'll find out exactly what that means. But right now, just say it does not mean spring return. Remember, we're Swiss, right? We're not American guys. We're Swiss. Okay. So here is the model number of the spring return actuator. So why do you think? Just guess. Again, those people haven't taken the course before. Why do I know that that's a spring return actuator? I mean, this is going to be a stretch, but I'm just asking. Okay. Well, the answer is this letter right here. F, right? So now the obvious question is what? WTF, right? Like why would F be designated spring return? And the answer is very simply, the Swiss word for spring starts with F. And it's as simple as that. Okay. You didn't know that? Is that right? You didn't know that? Yeah. All right, guys. So here's what we're going to do. This is where you got to hang on. In terms of the workbook, what we're going to do now for the next couple pages is we're going to go through and select this actuator right here. We're going to go through the process of how you would come up with this particular model. So just hang on, because it gets a little bit potentially confusing. But what we're going to do is we're going to go through all these different fields, and we're going to sort of verify this model number. The model number is AFB 24-SN4. Okay. So again, we're going to go through each position nomenclature. We're going to go through this sizing calculation for application and torque requirements, and then we're going to define the actuator. So first thing we got to do is talk about torque. Is anybody confused about what torque is, just as a general question here? So what's torque? If I had to say what's torque, how would you describe it?
Twisting force.
Force that opens my beer bottles.
Right. Well, actually, it's not force, but force is a component, right? Because it's not only the force, what's the other part of it?
Time.
The distance over which you apply that force, right? So like with a pipe wrench, if you have a short pipe wrench, you have less torque than if you have a longer pipe wrench. Why? Because you're applying the same amount of force, but you're at a farther distance away. So the torque is actually greater because torque is force times distance. So the answer to the question I asked is it's actually rotational energy or rotational work, however you want to talk about it. But it's that kind of thing. All right. So in this particular case, we're selecting an AF. Now the A stands for 180 inch-pounds. You notice here we have other selections here, right? We have EF, NF, LF, TF. They're just different sizes. So that first letter in Belimo nomenclature defines the size. And you can come up with your own mnemonic things for what A stands for, what E stands for. So again, even the people that write our presentations don't realize what torque is. It's not a turning rotational force. It's actually rotational energy. I've been trying to get them to change this for years. They won't do it. But anyway, so here's what I just talked about, right? If you have 1 pound force applied on a lever 1 inch from the center of rotation, you got 1 inch-pound. If you want to increase that torque, you either increase the force or you increase the distance on which that force is applied. In an actuator, how do we change torque? How do we get more torque?
Increase your distance.
Well, in an actuator, just like in a car, you have reduction gearing, right? So your gearing ratio determines your mechanical advantage, and that's like a lever, right? It's like a mechanical lever. So reduction gearing or gear ratios are equivalent to changing the applied force, changing the mechanical actuation. Okay. Okay, got enough of that. So here's the basic deal that we're going to go through now for this next section. We're going to go through an example that shows you get the damper area in square feet, and it's got to be in square feet. And we're going to come up with this torque loading factor in inch-pounds per square foot. So if you take the damper area in square feet, you multiply it by the torque loading factor in inch-pounds per square foot, you come up with the torque in inch-pounds. So 12 square foot damper, if your loading factor is 5 inch-pounds per square foot, 12 times 5 is 60. We're going to have our own little example here we're going to go through. If you forget what I said today and you want to figure out what I went through, on your book right there, the 2016 product guide and price list, this page is on 23.3, but it's also in your workbook. So you can use your workbook as a reference, or you can go to page 23.3 in that book and go through it. So follow along in your workbook. Here's what we're going to do. We're going to go through an example here, so you can write them down in the workbook, so you can keep track of what we're actually going through. The first thing we're going to do is figure out the area of the damper. So in this case, we have a 48 by 96 damper. That's in inches, right? So in order to convert that to square feet, what do? We divide by 144, right? Because there's 144 square inches in a square foot. If you know what a 44 by 96 is, you say, I know what that is. That's a 4 by 8. That's a 4 by 8 damper. So our first answer, our first fill-in is in the upper right on page 9 is 32 square feet. That's the size of our damper and face area. So what I'm talking about is just what we call the face area. What's another area applied to dampers? It's called free area, right? So what's free area, do you think? That's the area between the damper blades, right, that the air actually goes through. So engineers will talk about face area. They'll also talk about free area. So a certain damper type might have different free area, depending on the way the damper is constructed. But we want face area. So that's number one. Number two is, what is the type of damper? So there are two different types of dampers in HVAC. We use what we call opposed blade dampers or parallel blade dampers. Opposed blade dampers, if you've been in the field, you'll typically see them. Well, maybe I'll ask you, where do you see them?
Atomizers.
Atomizers.
Okay. Yeah, outside air would have an opposed blade. Typically, relief air might have a opposed blade. Anytime you want to control the throttling of the air, we call it throttling, right? We want to control that to a certain value. The registers in your house, right? If you have a heating system, those are opposed blade. So anytime you want to throttle the air and control it to a certain value, you use opposed blade. Parallel blade is typically used for either isolation service, right? Like a fire smoke damper, right? Boom, right? You got it open, want it closed. Or if you guys have ever been in these huge mixing bays, like in a big air handler, the ones you walk into, you'll see sometimes that the mixing dampers are parallel blade. For whatever reason, it seems to work better in the mixing application, so they use parallel blade dampers there. So, from a mechanical perspective, if you had the same conditions, the same flow rate, everything same, and you had a choice between an opposed blade or parallel blade damper, which do you think would require more torque to operate?
Opposed.
I think opposed, I'm gonna guess.
So why would oppose require more torque to operate under the same conditions?
Maybe more gears
Yeah.
to drive them.
in different direction. The other one's
Yeah.
just in one direction. Oh, right?
Yeah, so, well, the air could come from either side, right? So an opposed blade, you have some blades going with, some blades going against, right? Here, all the blades are in the same, take the same force, right? Well, the answer actually is opposed blade requires more torque because of exactly that. All of the force is applied to the same blades at the same time. Here, there's a net canceling effect because some of the blades will tend to open, right, with the force, and some would tend to close. So the net effect is that opposed blade requires less torque. And if you wanted to cheat, not really, but if you looked on the slide here, the opposed blade without any kind of seals is 3 inch-pounds per square foot. The parallel blade without any seals, the nominal torque loading factor is 4 inch-pounds per square foot. So that's about a 33% difference, just average, in the parallel versus the opposed. Just going to go through that. All right. So in our particular case, we have a parallel blade damper. So you can mark that off. The third question is, do we have blade and edge seals? Well, you guys work in older buildings, right? If you've seen the older buildings, you know that some of those old dampers, you can look through them, right? You can read through them, right? They have gaps on the side. They're like inch and a half. Nowadays, you can't buy dampers like that anymore, right? You have to buy them. They have to be AMCA tested, all that kind of stuff, so many sag pressure. But the question is, are there blade and edge seals on the damper? And that means, well, we know this, right? More sealing, more torque, right? Because you have friction involved with that sealing. So you have to answer that question. Well, in this case, we're lucky. We don't have any seals on our dampers. So we have a 32 square foot parallel blade without any kind of sealing. Number 4. Just recently, I got involved in this at a data center where the engineer did a calculation and said that he wanted a certain amount of, well, here's what he did. He looked at our calculations that I'm going through with you right now, and they figured out that they wanted a certain torque, and so they expressed it in terms of velocity. The damper manufacturer looked at the situation and said, well, our dampers have a torque loading factor that's much less than that. We're just going to provide ours. So here's the question. For the damper in question, what does the manufacturer specify as a torque rating? Well, if the manufacturer is willing to step up to this and you say this is what it is in inch-pounds per square foot, that's great. But what I would do, I would check their loading factor. I would check the calculation that we're going to do today, and I'd pick the bigger one. That's just me, right? Because then you can cover your butt. You guys may never get into that, but that's just based on what happened this last month or so. I would say this is a prudent path. In our case, we don't have it available, right? This manufacturer stuff is not available. So what we're going to do is we're going to go in and use our actual chart that is sort of universal throughout the industry for sizing. All right. Number 5, what's the air velocity, static pressure, design CFM? Well, of those 3 things, which one do you think would be the easiest thing to figure out or to get?
Design.
Yeah, this design CFM would be easier, right? Because you can find that on a schedule somewhere, right? You could find it, like on some engineer's schedule. You can find that. These other things, probably not as readily available. Sometimes you get the design velocity, but it's not always there. Well, in our case, we're going to say that we know that the design velocity is less than 1,000 feet per minute. But just bringing up the question for personal enrichment is, if you had to design CFM for a damper, how would you figure out what the velocity is? Because we're going to go into a table that has velocity. So how would you figure it out?
Any tap by the size.
Right. Well, you have the damper area, right? I'm looking for an eraser. Yeah. Well, here's there's the equation. That's sort of the general equation. So what it is, this is your CFM, right? This is your feet per minute, and this is your area in square feet. So if you want to figure out what the velocity is, you take your CFM from your design and you divide by the square feet of the damper, right? And that'll give you your velocity in feet per minute. Now, practically speaking, if you look at air handlers, say you get charged with like trying to put dampers on like a big ass industrial air handler or something like that, I can tell you just from experience that most of these are going to be velocity within a certain range. When I show you this chart, I'll sort of show you how that works. Here's the chart, and we're gonna actually, the chart that I want you to look at is at the bottom. Well, you can look at it on either page. Let's just look at it on page 10 because that's what the chart I'm showing you. A partial part of it is on the screen here, but that chart, if you look on page 10, it's got the 5 different types of dampers, right? Damper blades on the left. And then it's got 3 different columns there. And the first column is less than 1,000 feet per minute. That's the column we're going to be in for our exercise. But we got 2 more columns there. We got 1,000, 2,500, and we got 2,500, 3,500. All right. Any sheet metal people in here? Or former sheet metal people? No? Okay. No? No sheet metal guys? Sheet metal guys talk about duct in terms of pressure. So they say low pressure duct, medium pressure duct. Have you heard that term before? Okay. So just for to approximately this is true, these 3 columns here equate to low pressure duct, medium pressure duct, and high pressure duct. So just taking a break from this for a minute, where do you think you find low pressure duct in your buildings?
Registers.
Yeah. This is going to be, well, the velocity coming out there is relatively low. It's probably about 500 feet per minute out of that diffuser is designed right. The duct we're going up to, are these VAV terminal units here?
Gas packs.
Oh, they're gas packs, so they're constant volume, right? These are constant volume? Yeah. So that ductwork that's probably going back up to that unit is probably low pressure, or, like probably around 1,000 feet per minute, something like that. Exhaust fans, right? Toilet exhaust, typically low pressure duct, right? Maybe ½ inch, maybe inch of static, something like that. Where do you find medium pressure duct? Yeah, VAV, the primary air going from the unit to the terminal, the VAV terminal, is simply medium pressure. Maybe 2,000 feet per minute. Realize we're talking in this chart, we're talking about velocity, but medium pressure duct, it would be like 1,000 to 2,500 feet per minute. Most VAV systems are about 2,000 feet per minute, the way they design it. And the higher pressure stuff, probably unless you work in hospitals, you may not find that. I mean, industrial applications have what we call high pressure ductwork, but for the most part, we're going to deal with low pressure, medium pressure. Why do I mention this? Is because if you're looking at your system, you're saying, okay, I'm going to have to pull this one out of my rear end. Which one do I think it is, right? Which factors should I use? I would say if somebody puts a gun to your head, I would use these factors in the middle column, right? The medium pressure ones, because that's going to cover your butt. If you have openings in like existing air handling units, almost all of those are medium pressure. That is, they're set for like about 12 to 1,400 feet per minute. If you do the calculations on the velocity that typically goes through them, it's probably around 1,400 feet. Okay. All right, let's get back. And then high pressure, you might get a particular case on that, but it's not really as common. So let's get back to this. So now we're going to calculate the torque requirements for that 32 square foot parallel blade without seals with a velocity of less than 1,000 feet per minute. So 32 square feet. What's the torque loading factor if you look in that chart there? You can look in your book or look at it. What's my factor? You can either look up on the screen or you can look on page 10. What's the factor? 4. Should be 4 inch-pounds per square foot, right? Because it's a parallel blade damper without any kind of seals, and the velocity is less than 1,000 feet per minute. So it's going to be 4. 32 times 4 is 128. So that's what we call design torque. So now you know why we chose the AF, right? Because the AF is what? 180. So that's the closest selection that you have to that particular thing. So here's sort of a thing that's not on the menu, but I just mentioned it in passing if you ever get involved in this, is that, well, I'm going to say, in my experience as a design engineer, I always try to give myself a safety factor, right? I always want to put something on there for stuff that I don't know. And a typical safety factor on just anything would probably be 10%. So if you get within 10% of what you call your actuator rated torque, think about maybe going to the next higher size. But again, it's going to be a judgment call on how much you know about the installation. In this case, we're good, right? 120 inch-pounds calculated torque, 180, way oversized, right? And that's not necessarily a bad thing. Okay. All right. So we got our torque now. We're going to pick an AF. We calculated 128. We got 180. Now here's where you get the multicultural lesson. Okay. F stands for fader. So that means spring. That's it. That's all it is. If you have non-spring return actuators in Belimo, that second letter is an M for motor, I guess. I think that's probably a German and an English word. Have you guys ever seen our electronic failsafe actuators before? Anybody ever seen those before? What they are is they're capacitors built into the actuator that instead of a spring, the capacitors discharge and they drive the actuator to the failsafe position. The cool thing about that is that you don't necessarily have to fail them open or closed. You can fail them like a half open or 30% open or whatever. You can actually adjust the fail position. So K is for condensator, which is for capacitor. We make linear actuators with an H. I guess it stands for hub or hoob. I don't know what that Swiss word is. And then this little Umdrahung thing. This is some actuator. I don't think I've ever sold one in the 10 years I've been with Belimo. They call it universal rotation. It actually rotates more than 90 degrees, right? Because that's typically what we do, right? Our dampers are normally 90 degrees. This thing actually goes 350. And I guess if you took out the mechanical stop, it would probably rotate with a floating point signal, probably just keep rotating as long as you apply voltage to it. All right. So failsafe, everybody's clear on why we use failsafe, right? Or is anybody not clear? Why do we use failsafe actuation? Anybody know? What's that?
Power loss.
Well, yeah, somebody has decided, right, that when the power goes out, I want this valve or actuator to do something that makes me fail safe, right? Like, a really good example would be like a steam valve, right? If you lose your power to a steam valve that actuates it, what do you think you want it to do? You want it to go closed, right? In almost all cases, you want that valve to go closed. In Fairbanks, Alaska, their heating valves fail what? Open, right? Because theoretically, you can roll a boiler in on a truck, right, and hook up to the building and get heat in that building, and you don't have to worry about whether or not those valves are open. You're just going to run it balls out, and you're going to get heat into the building because it's not just a good idea. It's like survival in Fairbanks. So fail-safe is something dictated by the engineer or whoever designed the system and says, I want this thing to fail in a certain position. So let's get back to what we do. This is an air handler. This is just a diagram. We call it the H, right? If you guys have talked about this before. Outside air comes in here. Through a preheat coil, we don't see these a lot on this side, do we? Did anybody deal with preheat coils? So what we're doing is we're preheating the outside air, right? It doesn't usually get this cold here, so we don't use them.
Well, I'm for like runaround coils, for like if it on an exhaust fan.
Yeah, that's heat recovery.
Yeah.
Yeah, you could, normally that would be in this one though, right? It would be an exhaust air.
One in each.
Yeah, and you could actually transfer, right? So this is a preheat coil technically, or it could be outside air comes in this way, goes out to the space after it mixes with return air comes back, either circles back to the suction side of the fan or it goes out over the side. So if you were designing this system and you talked about fail-safe, which one of these dampers would be fail-safe, if any, and why would they be fail-safe? So outside air would be what? Fail-safe, and fail what? Open or closed? Right. And in this area, because we live in the Emerald City of Seattle, and they have Washington State, the energy code says, yes, it needs to fail closed, right? It needs to automatically close when that fan is off. Same thing for this guy, right? Anything that's in communication with the outside air around here needs to fail close when the air handling unit goes off. But how about this guy? How about the returner?
Well,
Yeah, if it's going to be fail safe, it would be fail open, right? And why?
so I can still recycle air, still heat or cool.
Well, yeah, that's one possibility, but there's another situation that this is more of like a.
Well, the fan comes on.
Fan
and it's
comes on,
closed.
heat air.
Exactly. If that fan comes on, and this is in some position other than open, like on morning warm-up, right? Morning warm-up, what do? We turn on the building, we circulate the air, outside air is closed, relief air is closed, we circulate the air, bring up temperature. If that damper fails in some position other than open, and that fan starts, what's going to happen? Collapsed ductwork, right? Ugly. That mixed air plenum has a significant negative, and it will. So if I was designing this thing, I would have fail safe on all three dampers. As you guys said, FC, FC, FO. And that's very typical, I think, of what we do. So electronic fail safe. Why would you choose electronic fail safe over spring return? Well, I'll be honest with you guys and say that we very rarely use electronic failsafe here for damper actuators. You know what I mean? For outside air. We don't normally use them unless we get to dampers so big that we can't deal with, with spring return, and I'll show you our product line in a minute. But one of the things about electronic failsafe for spring return, you can get more torque in a smaller package with electronic failsafe. You look at this, actually this is an AF and this is a GK. I'll show you one of these. The comparable one to this GK is an EF, and that guy's like this big. It's huge. That's the spring return, 270 inch-pounds, and it's this big. The GK is about this big, and it's about 360 inch-pounds. So you get more torque in a smaller package. We can, in some cases with electronic failsafe, we can have a faster runtime. Spring return actuators tend to be fixed on higher runtimes. We don't have that. We do actually have linear actuators that are electronic failsafe, which is, it's a really, I don't know if you guys know this application, but we did it down in Portland. We had a huge, well, we had a 40-story building with a penthouse. You guys don't even buy a penthouse, right? Built-in penthouse, walls of dampers, probably 35 feet high. They all were pneumatic plunger actuators. You know what I'm talking about? Those ones that are pinned at the end, and they're just plungers, and they were connected to drive clips on the dampers. What we were able to do is put in these electronic failsafe linear actuators, and we just dropped them right in. We dropped them right in, we pinned them at the end. It was bad. Now, if we didn't have those linear actuators that were failsafe, it would have been a pain in the butt. We would have had competing crank arms and things like that. It wouldn't have been fun. So that's a good application there. The adjustable failsafe I talked about.
Can you draw a picture real quick of the linear actuator since you don't have it?
No, I have one.
Oh, you do
I'll
have
bring it on the break.
there. Okay.
Oh yeah, you'll see one. Yeah. Yep, that's what it looks like. So this is a rack. Now this happens to be the non-failsafe linear actuator, but the failsafe one, which is the same, it's just got a different head on it. That's that odd Undra hung rotation actuator. Okay. Not Uber hung, but Undra hung. All right, I tell you what, we'll get through this guy. I tell you what, why don't we've gone about an hour. Why don't we just take 5 and be back exactly a quarter of an hour? We'll keep going. Want to get out of here by 8. Yes. Okay, is everybody back? All right, let's keep going, guys. Let's keep going. All right. Do I need a bullhorn or what? Yay! Let's start. Okay, thanks. Thanks very much. Okay. So let's start out with speed. So the speed, we have the torque rating here, AF, and we've got 100 inch-pounds. Now we're going to talk about speed. So speed, fast and slow, short story, are relative to the size of the actuator. So it depends on like what size it is based on whether it has a fast or a slow. Not all actuators have a C, fast running or slow running. It just depends. Most of the times they're the smaller ones. For instance, if you look at here, we have like a TFC and an LFC. That means they're fast running. Fast running turns faster than normal. What's normal? Depends on the actuator size. L, slow, relative to the nominal size. In this case, our slow rating, I think our TFLC is 75 seconds. It's all relative. If you want to know what the speed is, you go into the catalog and you look under the product offerings and it'll show you. Let me show you where it is for the spring chart. If you go to chapter 1, if you go to page 1-6, 1-6 has the LF and the TFB series. If you look at that, let's see, the sixth column, it shows you the drive time. So that's the drive time in terms of seconds. You know, some of them are adjustable. Those are programmable actuators, but that's what I'm talking about. So if you want to know how fast the thing runs, well, if you're looking at just a regular actuator, it'll tell you on the face of the actuator what the speed is. So that's more of a practical field thing. Okay? All right. So in our case, we got nothing here. So that means it's whatever the normal speed is for the AF. Okay? You can look that up. This is the thing that confuses a lot of people with Belimo, and about 10 years ago we went to used to be just AF24. Now it's either AFB24 or it's AFX24. So I'm going to try to explain it to you here. It's fairly straightforward, but I just want to make sure that everybody understands it. In this case, we have an AFB. B just means it's a basic product. It means we stock it on our shelves, we make them up, we put them on the shelf. You want one, we ship it to you. No, nothing else done. And X, if it's an AFX or an EFX or whatever it is, it means that somehow we customized it. What does that mean? If you go in the catalog, if you go to page 1-7, for spring return actuators, this shows you some of the things that we do for customization. So, if you look at page 1-7 in the catalog, you can get a crank arm installed on the actuator if you want. You don't have to put it on yourself. Number 2, you can get cables. You can get plenum rated cables. You can get 10-foot cables, 16-foot cables. We just had a project down in Portland where they want 10-foot cables on all the terminal units. They don't have to run to a junction box. They're going to go straight from the controller to the cable, to the actuator. You can, if you look on page 1-7, you can see we have programming codes. Those are for the programmable actuators. You can get some hairy programming code, and that would be an X. Here's what you need to know from the field standpoint. If you have an X actuator, right? If it says X on it and a model number, on the face of that actuator is what they call a reorder number, and it says reorder number, and then it has a bunch of letters and numbers. That is the factory code. It tells us exactly how we made it. You don't have to guess. You give them that code. You give MI the code. They know exactly how we made it because it may not be evident how it's special. Okay. All right. So we have an AFB. What's that? What's that?
That code means you have to call carrier. You can only get it through carrier.
Oh,
train or whoever yours.
No, well, for Belimo, what it means is that you got to call MI if you don't know what it is, right?
Well, I'm saying when you call them, they'll be like, "Oh, we can't find that number anywhere."
Well, MI can always find it.
They can always find it, but they can't always get it.
Well, you're getting the OEM stuff, which is a different thing. You're right. All right, so AF. Now we're talking about power supply. Power supply is really easy, right? Because it's either 24, 120, 230 we don't use, right? One thing you want to note, if you're dealing with two position actuators, for the most part, there's this thing called a UP, and it's a universal power supply. It means that it's an auto transformer, and it switches for what voltage is applied to it, from 24 to 240 volts. You don't have to, the electricians can never screw you up on that one, right? Well, they could if it was 482.77, but then you have another whole set of problems if you have 482.77. So, but this one is actually, it's a universal power supply. Again, it's only available for actuators on two-position actuators or open, open close, not proportional. Does everybody know what I mean by that? Yeah. Okay. All right. So in this case, we have an AFB 24. So it's 24 volts. Well, AC or DC. I just mentioned on that in passing. The AC, we all use AC transformers for the most part, right? It's all 24 volts AC for the most part. What happens is the actuator converts that to DC. When he brings in, it goes through rectification for the electricians in the bunch here. But you can provide either AC or DC voltage to these things. So if you're on a shift, it would work. Okay. It also goes 24 to 125 volts DC, although nobody really ever uses that, I don't think. Control signals. Now here's where we talk about how is the actuator actually controlled. In our particular case, the field is blank. This means it's two position, right? It's just on off. But you notice we have some other options here. And so if we look at the different options, if you follow along in your workbook, on page 12 and 13, we talk about some of the different control signals that are possible, or I guess these are more of the, at least three of these guys are probably 90% of what you guys are going to see out there. So the first one is, I call this two position because I think on off is probably misleading. You guys know what I mean by two position, right? The actuator drives to one position or goes to another position by any different means. So if you have a spring return actuator that's two position, how many wires do you need to operate? Two, right? Because all you're going to do is drive it one way, apply the voltage, and then take the voltage away, and the spring takes it back the other way. That's two wires. How about for a non-spring return? Three. Now we need three, right? Because now we got to drive it either direction. You have to drive, the motor has to drive in either direction. So this is as simple as it gets. On off. Floating point is, well, anybody know what floating? Who can describe floating point to me? For those of you guys that have, what is a floating point signal? How do you get it done in the field? Okay. I can see those of you that took the course didn't take. So. What's that? Well, let's just use something that we've learned supposedly. What kind of outputs are required to operate a floating point actuator? No. Oh, next question. Next answer. You need two digital outputs to run a floating point control. And what you do is you close one digital output, apply 24 volts, say. The actuator drives in one direction. If you close the other digital output, it drives in the other direction. If both digital outputs are open, then it doesn't do anything, or it stays where it is. And that's why we call it tri-state. Because it's either driving one way, driving the other way, or it's at null. One of those three states is what the actuator is in at all times. Used for VAV boxes, like if you guys work on VAV boxes, you've seen this signal, right? This is what that signal is. It's typically a floating point control. And one of the reasons for that is that it's less expensive. You don't need a fully proportional signal to run a VAV box. You just what do you care about? Discharge air temperature. That's all you really care about. Huh?
I came back.
Okay. Just tell me I need to take a break. Okay. So the third one, on-off, easy, right? This would be a single DO, right? You could actually run this with a single DO, right? This, two DOs, right? this is the one that needs the analog output, proportional control. So proportional control would be an analog output from the controller. It could be 2 to 10 volts, 0 to 10 volts, whatever it is. Typically, for us, our proportional control signal is 2 to 10 volts DC. That's how we run it. Now, with proportional control, one of the advantages of that is, if we go back over here, I can command that. I can command the actuator. This is an analog output. I can command that actuator to a specific position, and the feedback can report it exactly, right? Just like in the data centers. Proportional control and feedback sort of go together, right? Because you can command the actuator to a certain position, and you can confirm it's in that exact position. The fourth signal, this one isn't used as much, but you might see it out in the field. It's called pulse width modulation. If you're in your workbook, it's at the top of page 13. This one's a little bit, it's interesting, so I'm just going to show you what it looks like. So, just say you got, this is a 24 volt power supply, okay? You've got voltage here and you got time here. So, if you have a pulse width modulation signal, just to say it's 0 to 10 seconds, so that represents the width of the pulse. Well, we know we can't have a 0 width pulse, right? So we got to have something that's minimal, like a 1/10 of a second, say. So we got a 1/10 of a second to 10 seconds. That's the range of the pulse width. All right, so if we have this actuator, we give it a 2-second pulse. We close that digital output for 2 seconds. Where do you think that actuator goes in its range in terms of percent? Approximately 20%, right? 2 seconds, 20%. Okay. So at some other point, that digital output closes for 4 seconds. So where do you think it goes now? 60. 50? 60. 60? It actually goes to 40, and that's the beauty of it. Because what's going on here is the actuator maps the width of the pulse to the position that it takes. You see what I mean? So it only looks at the last pulse. It looks at that pulse and says, okay, that's where I'm going, right? So if you want to close it, or whatever, bring it to minimum, you give it a 1/10 of a second pulse, and it drives to that position. So here's the cool part about this. You get sort of like a positioning control like you do with analog, but you do it with one digital output. So why is that a big deal? It's sort of a big deal because this happened to one of my customers. He had a spec where the engineer called for proportional control, so he called for this one. Full analog output, right? He called for fully analog. The controller that he specified or that he submitted for approval didn't have enough analog outputs. And that happens, right? You might run out of analog outputs on that controller. So I said to him, I said, well, try pulse width modulation. Maybe he'll take it. So that's what it actually saved his butt because he would have had to replace all the equipment and get another, and actually upgrade his controller. So it worked out good. I mentioned it to you guys because you might see it in the field and say, well, what the hell is this? Well, it's called PWM. Now, I don't know if you guys have heard of it. Where is PWM? Have you heard that term PWM before?
Yeah, VFDs.
Right, exactly. Now, with VFDs, what happens is, with VFDs, you're trying to generate that sine wave, right? You're trying to generate the frequency. So you generate that frequency. What happens is pulse width modulation there is used where a wide pulse is a higher voltage and a smaller pulse is a smaller voltage. So basically what you're doing is you're trying to represent the frequency by the width of the pulse. And that's the way, and actually it's a lot cheaper to do that than with like we call our old inverter drives and things like that. That's what made, the pulse width modulation drive is what made the VFDs affordable by the technology that they used. They were actually able to get commercial grade VFDs done a lot cheaper. Okay. But pulse width modulation in controls is this, where the actuator only remembers the last pulse and it maps that width of that pulse to a position on the actuator. Phase cut, you guys are probably aware of this signal if you've ever seen it before. McDonald Miller is the STAFA, the STAFA guys here in Seattle. I'm not going to spend a lot of time on this except to say it's a signal that's going away, except maybe for you guys. You guys still have to deal with it somehow, but nobody else deals with this anymore. It's a signal where what you're looking for is a current draw over some portion of the voltage cycle, and the actuator maps basically the current draw over the cycle to a position on the actuator. Very similar to this, only now we're using current draw over a voltage cycle. It's probably a pain in the ass to deal with. I've never had to deal with it, but it's going away. Most people, when they see the phase cut thing, most of the time, and you guys are probably doing this too, will convert phase cut to proportional control. That's typically what's happening. They go to a 2 to 10 signal. And then MFT or multifunction technology, this is more of a technology. It's not really a control signal. It's really something where well, I'll give you a mechanical engineer's definition of this. It's a fancy motor controlled by a chip. So the chip can be programmed, and that chip can make this actuator like an on-off actuator, a pulse width modulation actuator, floating point actuator, a proportionally controlled actuator. You can change the runtime, you can change the torque, you can change the angle of rotation. You just program it, and it changes the rotation. Good example, you guys maybe never have crossed this. We had a data center where the mechanical contractor decided he would provide dampers that from full open to full closed were 45 degrees. Whatever, right? I mean, that was the stroke angle, right? It was a 45-degree stroke angle. Well, the control contractor got on board and said, what? I mean, why aren't they 90 degrees, right? Well, good news was they got our MFT actuators. They programmed the stroke angle for 45 degrees. It was good. Didn't have to buy new actuators. Just got the MFTs. So it has some uses. It has some uses. We use MFT actuators on our valves, where what we do for our pressure independent valves, our smaller ones, is we might have like a 3/4 inch valve that is programmed to operate, designed from 6 to 10 GPM. So all we do is we limit that rotation angle based on the flow rate that goes through it. And we can get one valve body and program it for a number of different flow rates. So that's how we use it on pressure. Now, as far as the other ones that you might be interested in, we've gone through floating point. Here's the SR. I didn't point that out. SR. Okay, the German word is, well, it's 2 words. Stetig regulator. But for your purposes, all you need to know is SR in a model number of a Belimo actuator means exactly 2 to 10 volts DC control signal. It doesn't mean anything else. It's not 0 to 10, not 0 to 5. It's exactly 2 to 10 volts DC. So that's what SR means. For your guys, a lot of people you guys work on package units, right? Like rooftop package units. We make a control signal. It's actually an LF24 Econ R03. This one is a specific signal that's made for it's basically a actuator that's a retrofit for a 7415 Honeywell. And what it does, it takes a 3 k ohm input, which is the mixed air signal, and it positions that actuator based on that 3 k ohm input. So again, it's a very specific actuator. These MFT ones, this is generic MFT. This MFT in 95 and 20, these are specific actuators, as I mentioned. MFT 95 is for the Honeywell Series 90, and the MFT 20 is for the old Barbara Coleman beer can actuators. If you guys have ever come across those are going out. We're replacing them with whatnot.
Is that Econ R3? Does that have that same square base as the?
Let me show you what it looks like. Let's go to retrofit. See, the retrofit section is chapter 21. See if I can find it here for you. It's on page 21-6.
I think just like the old Honeywell square.
Oh, yeah. Yeah, it's a replacement for a mod control. So if you look on page 21-6,
Oh, so it's got an adapter plate.
Yeah, you can get like an angle bracket. You can get spade connectors. There's actually kits that come with that LF24 Econ 103. So what they're showing you here on 21.6 is they're showing you the actual, the actuator itself, and then you can get a kit with a ZG Econ 1 or a ZG Econ 2. And that replaces the 7415. And then there's two other solutions there with regard to.
That's a hell of a lot cheaper. That module control.
Again, these are list prices. Unless Tom is really mad at you, he's not going to charge you list price.
No.
Well, I don't even think they make those black Honeywell anymore.
Really?
Because I tried to get one for a carrier unit, and they don't even have. They sold me that.
Yeah.
Oh, you mean the Mogitrol, you mean?
Yeah, they couldn't even get it.
Yeah. Well, I don't know what Honeywell's doing with those. I know that let's just say you guys are troubleshooters. From talking to the guys that work on them, they're a little bit hard because they'll check out okay, but they don't work. Right? So that's always frustrating, right? It checks out okay, but it doesn't drive. So that's always a problem. It was from a troubleshooting standpoint. So anyway. All right, so let's get back looking at our position 7 here. We had a -S, right? So a -S in the model number means that you got a built-in auxiliary switch. Do you guys know what I mean by that? It's actually a switch inside the actuator that does what?
Closes when it's to its position.
Yeah, so what happens is that actuator will rotate through its angle of rotation. You can set that switch to make at a certain rotation angle. Why would you want to do that?
Maybe for like a water control valve, that condenser water, you want to wait
Bring
till
a
your
fan on with a damper open.
Right, that's probably the most common thing. You're right, that's true. You just want to know at a certain angle rotation, you're gonna close that switch. You're gonna energize the control relay, and like you said, that control relay is going to be in the start circuit of a fan. And it's going to bring that fan on at a certain open position, or shut it off at a certain closed position. One or the other. Okay. So we make a -S. We build them right into our actuators, right up here in the corner. On our non-spring return actuators, we actually make a -T, which is a terminal block, which instead of a cable whip like this, we actually have a terminal block, and you can wire directly to the actuator. You don't have to go to a junction box. And sometimes that's advantageous to do. You don't want to have to go to a junction box. You can wire straight through. And we do have, like, for this particular actuator, we have like a little cover that you can put on that thing to make it look like it's, well, I guess just sort of finish it off rather than having the cover blocks out and flapping the breeze. All right, so we've gone through our whole, almost all of our fields except for one. We have an AFB24, 2-position actuator with a built-in switch, and then over there on the far right is N4. So N4 stands for NEMA 4. What's NEMA 4? What does that mean?
Enclosure constructed for either indoor or outdoor.
He's reading from the book. Yeah, so what it means is NEMA 4 is an outdoor weather enclosure for around here, right? We got, you can rain on it, you can sleet on it, snow on it, you can probably pee on it, but what it's designed to do is keep the actuator protected from the weather. So we make a NEMA 4 and we make a NEMA 4H, which means you can actually get heaters put in these things. So around here, we don't use them so much, but where would you use heaters? Alaska, right? Anchorage, anyway. Yeah, you can use them in Alabama for what, though? Why would we have a heater in Alabama?
Condensation.
Hey, guys. Oh, no. Right, thanks. Yeah, for condensation. Right. So in Alabama, you get condensing temperatures inside the actuator. So you keep the temperature up so you don't hit dew point, because you don't want to hit dew point inside the actuator. So this is actually just a regular old N4, and that's what it looks like. I think I've got one with me. It's a big ass enclosure for this particular NF. It's probably about this big. So, and actually what happens is, I think I've got one with me. You bring the damper actuator goes in the back, and it's like a well, and the clamp is on the back. This is just a position indicator that shows you the rotation of the damper shaft. What this gentleman was reading from is this page right here. These are some of the NEMA definitions. For our purposes, we use these three. We use NEMA 2. That's our normal actuators that are indoors. We use NEMA 4, which is what we just talked about. This would be for enclosures around this area. And then we have a NEMA 4X, which would be like Aberdeen, Coos Bay, marine environments with salt, corrosion resistant, or a swimming pool, right? If you have like a natatorium or something like that, you could use a NEMA 4X, and that would be corrosion resistant. All right, so we went through these before the break, right? 32 square foot, parallel blade, no seals, less than 1,000 feet per minute. So that's the first half of this actuator deal. The second half is now we got to figure out what the actuator is. Like what's the specification for the actuator? So let's go through it. So for our particular application, is fail-safe required? Yeah, and we have an AF, right? So the answer is yes. And this, if you're in the workbook here, you're probably yeah. So 15 is fail-safe required. Yes. What's the supply voltage? Easy, 24, right? We got 24. What's the control signal? Number 8. Right, on off. Moving through. Can you direct couple to the shaft? Well, in this case, I think we're going to say yes, right? But what happens if you can't? Yeah, you need some accessories and things like that, right? One of your you guys have an installation up on Capitol Hill. I think what's the
Madison,
no, it's the college up there. What's the college?
Seattle Central.
Yeah, you guys actually have an interesting installation up there. You have what we call our jack shaft linkage adapters. And I'll show you what it looks like in a minute. But I walked in there because I think they wanted to show me how well they worked. But guess what? They got Honeywell actuators. That sucked. I'm joking. It was okay. But let me show you what this linkage looks like because I think it's going to be it's something that you may see a need for, and it's sort of slick. So go to page 5. We'll go to the beginning of page of chapter 5. You'll see Nadia there jumping up and down on a jump rope. And if you flip the page and don't look at Nadia anymore, you'll see that on the left. Yeah, go ahead. Flip. See that? This page right here with the jack shaft linkage adapter? Yes, it's behind Nadia. So you see how that thing works. It's basically like a rig where you bolt, if you have a jack shaft, you can bolt that linkage to the jack shaft, you can bolt the actuator to the linkage, and then it saves you about an hour of time, I would say. How many people have ever had to take off a jack shaft in order to direct couple an actuator? Anybody have to do it? Yeah. It's a pain in the ass to do. And you may not even have room to even get it off. So this is one way, sort of like I call like a mid-ground on direct coupling. I didn't ask the question, but I'm assuming that when I say jack shaft, does everybody know what I mean by that? Okay, so what a jack shaft is, you look in that picture, the jack shaft is what that linkage kit is on. And that can extend over different, you can put multiple sections of dampers on a given jack shaft, up to about maybe 12 feet, something like that. So what happens is you use the jack shaft to actuate all the dampers at the same time. It's a pretty common installation. In our particular case, we're going to say, yes, we can direct couple. And you guys know if you can't direct couple, you can call MI, you can call me, I'll give you guys all my card before we leave, and we'll figure out a way to get it done. And then finally, are there additional accessories required? Well, in this case, we're going to say yes, because we have the NEMA 4, right? Remember that NEMA 4 enclosure? That's considered an accessory, I guess, or a add-on to the basic offering. All right, so let's go back through it again and beat the dead horse. We got a 32 square foot damper with parallel blade with no seals. The actuator torque is 128. So we picked an AF, and we have a fail-safe 24 volt, 2-position actuator we couple to the shaft, and have a NEMA 4 enclosure. Here's all the data. that we just talked about. Ta-da. As I said to you guys before, I'll editorialize a little bit. This is agonizing, but hopefully, I'm more of a modular teacher. But anyway, that's what we did. Okay. So what I want to, I know it's a little bit premature. We just took a break, but I got to haul my stuff in. So why don't you guys just take 5, and I'll bring my stuff in, and we'll start the next session.
You ready?
Yeah. All right, I know this has been a long day for you guys. It's been a long day for me too, but we're going to try to get through this as quickly as we can. So I don't want to have to start throwing stuff, but in the Navy, the instructors got to throw stuff at you because you're just a piece of meat, but I don't want to resort to that here. You guys aren't indentured servants. All right, so actuator types. I've actually got representative types of most of the actuators that we have, and we're gonna talk about. We're actually going to deal with some of them in the lab, so I'm not going to go through every one of these. I am going to show you some of the more highlighted ones, like for instance this EF. You guys have probably, I don't know if you guys have ever seen this one before, but I call this the big ass spring return. So this one, if you guys have dealt with Belimo for a while, you probably remember an actuator that looked something like this, right? This is an AF, okay? This happens to be a fire smoke damper AF, but it's still an AF, okay? An old 133 inch-pound spring return actuator. The EF here, it's 267. So the little, the higher math says one of these is equal to 2 of these. So the reason I'm mentioning this to you guys is if you see an installation where you have 2 damper actuators like this on the same shaft, my recommendation is replace it with one of these.
What's the price difference?
It's pretty comparable. In fact, I think this is a little less expensive than 2 of these. And actually, we don't make these anymore. So you would have to have 2 AFBs, which are 180, which is actually more torque than you need. So, but I think when we had these available, I think for practical purposes, this was slightly less, like not by much, but it was definitely less because the idea was to, to go to the newer technology. That's not to say, recognizing what you're saying, that we don't upsell at times. I mean, that's a natural thing, which frustrates me, but that's what we do. So that's the EF. So I want to show you some things on this actuator that are common to all spring return actuators. But I want you to look at it when you pass it around because we're going to use this in the lab. The first thing is, on each side of this actuator, there's a rectangle with a spring in it, like a coiled spring in it. And it has CW on one side, and it has CCW on the other side. So what is that? Clockwise and counterclockwise. But what does it mean?
Spring return.
It's the direction that the spring will rotate when the power is lost, as you look at it, right? So if you see clockwise in front of you, the power goes off, that damper's going clockwise, okay? And conversely, if you look at it, it'll go counterclockwise if it's flipped over. The other thing to note is we've got a switch down here, and I want you to look at it when it goes by. This switch has 2 positions. It has a y equals 0 with an arrow pointing that way. It has a y equals 0 with an arrow, circular arrow pointing that way. So what do you think that is?
Where it gets direction of drive.
It has to do with the drive, you're right. It has to do with the 0 or the minimum position of the drive signal. So for instance, if the arrow is pointing this way, what it's telling you is that the minimum position of the control signal is all the way clockwise. And this switch means it's all the way counterclockwise. That refers to, just to give you a clue here, that's going to set the normal position of the damper set, okay? This, which side you have facing you, is going to determine the fail rotation of the damper system, okay? So we got normal, we got fail. 2 different things entirely, okay? There's a manual override on this. I'm looking in my box. I think maybe the hand crank isn't in here, but this actually has a manual override where you can actually crank this thing open when it doesn't have any power. It's about 20 turns to go 90 degrees. So
you can look in the middle here, there's like a little hex wrench. I think this is a 5mm hex. So you could use it with a drill if you wanted to save yourself the hand cranking. It's a 5mm hex, and there's a switch here that allows you to lock it. So you can crank it open, lock it, it'll stay locked as long as the power is off. Okay? What happens is if the power goes on, I believe this unlocks, right? It'll drive past it and unlock it. But while the power is off, if you need to open that damper, you can crank it open with that. All right. Finally, the actuator itself, if you look at it, actually somebody put the clamp on in the wrong place, but the side of the actuator gives you the indication of the rotation, right? You look on the side here, it'll show you. And this rotation is actually in degrees of rotation. So it's 0 to 9, actually 95, right? So this is a 95-degree rotation actuator. These things are pre-tensioned when we first ship them in the box. So what happens is if you follow the instructions and you seat this actuator on the shaft, you seat it, you close it, keep it closed. When you turn the power on, it releases, and what it will do is it will go and seat the damper blade. It's about another 5 degrees of rotation, so make sure that damper seal is tight. So it's a way to install it to make sure that the dampers are operating properly. If you look in the upper corners of the actuator, you notice this has 2 cable whips, right? One's for power and signal. This is the power and signal cable. This is the switch cable. So the switch, if you look at it, it's adjustable up here in the front. I think the fixed rotation of the lower end is 10 degrees, and then you can adjust it from 10 to 85 on the upper end. So that's how you set it in the field. So this is an EF B24SR-S, so 2 to 10 volts with an auxiliary switch. The LF is we're going to deal with in the lab, so I'm not going to show you that one. I'm going to go on to the electronic failsafe actuators because you might see these, or at least if you never saw them before, you're going to see one today. So this is electronic failsafe. Remember I told you the EF was 270? This is 360. So it's a smaller package, more torque than that one I just showed you. Sort of looks like a dually here. You got the wide body actuator. The capacitors sit right here. So those capacitors sit inside. If you look on the switch on the front, there's a little plastic window here. This is where you adjust the actual fail position of the actuator. You can set it to be in 10-degree increments all the way from 0 to 90. And the other thing that's cool about it, if you lost the power, if it drove to the fail position, whatever it is, as long as that capacitor has power, it will drive, right? So you can actually, move it if you felt you needed to move it. The clutch on these, now the Trim-return actuators do not have clutches. They have manual overrides for the larger ones. This one has a clutch. So if you push in this clutch, now I'm disconnected, right? I can move it anywhere I want it. When I lift up that clutch, now I'm locked in. Okay. If you notice here, actually that also has it. We have mechanical stops on either side if you want to constrain the motion of it. There's also a direction control switch on this actuator, only this time it doesn't say Y = 0 clockwise and counterclockwise. What it has is just arrows that go clockwise and counterclockwise. They mean the same thing. They mean the same thing in terms of the proportional actuator. This thing right here is a programming socket for the MFT. Not really to worry about unless you get into that. And notice here, and I think it's on a lot of our actuators, we have a wiring diagram right on the cable width. So in case you know what does red mean, what does white mean, how it actually get wired, we have that. So this is the GK B24SR. So this is the proportional electronic failsafe. I cut the cable off. This is, remember I told you about the linear actuator? So this is a linear.
What's the status?
Huh?
Status?
Yeah. That's for driving. And then if the capacitors fail, it will show you that they have failed. So maybe I think we said the life on our capacitors is about 15 years. And so far we've been out for 7 years, and I don't think I've had any failures in my territory. So hopefully that's good. All right, so this is This is an AHKX24MFT. So this is one of those fancy programmable actuators. Now it's an X, right? So you can look on the side of this, and you can look on the face of it. You can see the reorder number. I want you to just note that as it's going by. And, yep, the reorder number is all legible and that will be read. Same thing here, except now when you push in the clutch, now you got linear motion. So this is like a 4-inch stroke. So depending upon what application you have, one of the things that you teaching a class or am I? All right. So one of the things you can do with this, again, you got a pin here on the end. What we did on that project I told you about is we basically rigged a flat plate on here, bolted it to that, and we're actually able to mimic the pneumatic actuator stroke. We're actually be able to drop right in. It was great. It was a great retrofit. Anyway, so if you never see one again, here's a AHK linear electronic failsafe. All right, so that's the second one here. So what I showed you was I showed you this guy and I showed you this guy. This one here is an NKQ. Now Q is for quick, just so that you know what's going on here. You remember we had C and L. So Q is for quick. That sort of makes sense, right? That's English. The NKQ, and I know this is a lot of information for you guys after work, but this is a quick acting actuator. I think it's like a 4-second stroke. It's pretty amazing, right? I mean, it'll go 90 degrees in 4 seconds. So the applications you guys might run into where you might want to use this would be like on, well, maybe I'd ask the question, have you guys ever done like a fume hood control? You guys involved in the schools? You do like fume hoods or something like that?
Restaurant.
Yeah, well, they don't usually have dampers on them. Yeah, they're normally like type 2. They have
Biomed.
Yeah, Biomed. These are 4-second. You can potentially use them for makeup air, like fast acting makeup air, or things like that. You just have to look at the application. But we use them on dual duct boxes. I don't know if you guys are familiar with those. That's an older technology where you have like hot air and cold air. They go out to the terminal and they mix them in the terminal unit. Seattle doesn't like them very much. So
There's a few of them.
what?
There's a few.
Yeah.
Still around.
Yep. So we have that, and that's also electronic failsafe. Okay, how many guys deal with fire and smoke damper actuators? Bunch? Yeah. So here's the full line. This is the I have this is the only one I have here today. This is actually an FSAF 24SR. Oh, wait a minute. I said that was an FSAF 24SR, right? So what does that mean? What's the control signal on this?
2 to 10.
2 to 10. Aren't fire smoke dampers all 2 position? Why would we have a fire smoke damper actuator that's 2 to 10?
Dual purpose.
Dual purpose. So what you can use this on, here's a good application. And say you got a multi-story building, and say you got reliefs on every floor, right? You have a relief damper on every floor that returns the air. You can control the relief air to that damper, to that air handling unit, and install that right in the shaft wall, right? You know that damper that's right in the shaft wall that's rated? This can go right in that damper. It can actuate the fire smoke damper to control the relief air, and then also, when it becomes a fire smoke damper actuator, it's got to close, and it closes. So it's a dual purpose, like you said, dual purpose actuator. But you notice here we go all the way up to 180 inch-pounds, up on the big guy, the FSAF, and we go down to little guys here, the FSTF. Now, I want to say something about these fire smoke damper actuators. These are specifically for what? Life safety stuff, right? They're only made for the fire smoke damper assemblies that you guys have in the buildings. How many people have ever replaced fire smoke damper actuators on existing buildings? How many people have done it in Seattle?
We're not supposed to.
Okay, so the jurisdiction has always been okay with that? Or?
Well, normally
We
it's
just we do it for our customers.
yeah.
You beg so you beg forgiveness? Well, no. I'll be honest. No, I want to. This is important for you guys, so I want to make sure that you guys all know this because you guys are going to do this from time to
I think
time.
most of the time it's the Honeywells with the Honeywells, unfortunately.
You have to replace. Like,
Well, that's not necessarily true.
Well,
I want
I always thought if it was in the ductwork and it was, could be exposed to, say, heat or fire, then it has to be a like for like. If it's outside the ductwork on the shaft, you could get away with doing a Belimo.
Okay, here's the most. This is one of the most important things you guys are here tonight. Okay, here's how it works. The UL, now the fire smoke damper assemblies that you guys work on, those are what they call UL listed, and they're UL listed 555, 555S. One stands for fire, one stands for smoke. They have a specific UL listing. Okay. The UL does not address maintenance, right? So what happens if something there fails, right? What do you do? The UL does not address maintenance. They just say it needs to be operable. So technically, if you replace the fire smoke damper actuator on an assembly, you have technically violated the UL listing. So how do you get back all right with the universe? The way that you get back all right with the universe, at least in our experience, we've done many of these, thousands or millions of dollars, is the jurisdiction, either the fire marshal or the building official, has to say, yes, you can replace that actuator with that actuator. Now that could be Honeywell for Honeywell, it could be Belimo for Honeywell, it could be whatever it is. They need to basically, they're the ones that restore the quote UL, if you want to talk about it that way. Now, how do you do that? As you guys know, you can ask permission or beg forgiveness. Like in life safety, it's probably better to ask permission. I mean, in terms of what they approve. But if you guys ever come across this, the city of Seattle has been very good with us. I know MI has done a lot of business with Seattle School District. They have replaced some of their fire smoke damper actuators. Things have happened. You guys have probably done them. We've had no problems with the city of Seattle as long as you obviously follow you know how to put an actuator on a shaft. We haven't done this. But if you ever get into trouble, we have one jurisdiction around here that balked on us. They said, nope, you must replace that actuator like for like, right? Like for like. I got a chuckle out of it about a year and a half ago. That same jurisdiction relented and let the owner put in Belimo for replacing the fire smoke damper actuators after 8 years. And I think probably what happened was that the existing equipment kept failing every 2 years, and they got sick of replacing the dampers. So they finally came over to our side. But I want to say, if you guys ever get involved with a jurisdiction where they say, no, you can't do that, or something happens, we've been pretty successful in working with those guys and convincing them that this is okay. I mean, if they just flat out say, no, there's nothing we can do. But I can tell you, in 10 years, I've only had one jurisdiction balk at us and say, no, you can't do it. And no, they shall be nameless, but if you work in that jurisdiction, I'll be glad to. Yeah, we have some jurisdictions around here that are pretty interesting, like the city of Bellevue. I don't know if you guys know this, but when I was an engineer, they made me line up all the terminal units so that if you open up the terminal unit, that it would be in line with a 2x4 grid. After the fact, after we had designed the whole thing, they made us reorient all the terminals. So, and Linwood did an imaginary ceiling on me. So the imaginary ceiling was, we had a storeroom, went up the structure, no ceiling. Had a ceiling in the retail area. They said, well, you have to sheetrock this whole thing because, I said, why? I said, because there could be a ceiling here. I said, but there's not. And he goes, but there could be. I said, but there's not. And they made us sheetrock the whole thing. So, yeah, jurisdictions. Huh?
I said there's a possibility of a lot of things. Just you can.
That's right. That's right. Well, the architect is looking at me. I'm like the mechanic. The architect's looking at me going, John, what's he saying? I go, he's saying we got to sheetrock it, right? Anyway, so, yeah. So non-screw return actuators, I got a couple for you here. This is the big guy. This is the GM. So this is 360 inch-pounds, like the GK. Now these guys, you probably see more of these. One of the things about these guys that I want to show you is that they have a clutch, right? See how the clutch goes? You can push this down. If you push this pin in, now what I've done is I've actually locked that clutch in place where I don't have to put my thumb on it. But remember, this does not unlock. This does not unlock, so you have to make sure that you push it before you leave. Otherwise, you'll be out of control. So, again, this is a GMX24SR. It's got a reorder number on it. Take a look at that. For you guys that deal with our product in the field, this is probably most of what you'll ever see, right? You guys recognize this guy? Probably used on VAV boxes. For a VAV box? This is 45 inch-pounds. Anyway, so same thing. Still got the manual override. I mean, got the clutch on it. This one's got the turbo block on it. Like I told you, you can wire directly to it. It actually has a little cover that goes over it. And this is the probably not quite the littlest non-stream return actuator, but almost. I'll show you the littlest one. This one you will probably never see, but maybe you will see one day. Yeah. So this is called the CM, and I call it C for cute, right? Because it's like tiny. Pretty small in terms of footprint that way. You guys use VVT? You guys work on you guys know what I mean by VVT systems, changeover bypass systems? Where I've seen these used is using floating point on those little quadrant dampers that are in the zones. It works pretty well, like particularly if you don't have a whole lot of space. I don't know what the maximum shaft size in this, I think, is like 3/8 or something like that. But one of the interesting things about this has a magnetic clutch. So here it is. It's okay. It's engaged, right? So if you put this on here, now you can get it. You have to get it to engage here. So now the clutch is engaged, and now I can move this. And now when I take it off, I can't. Again, probably not used a lot in commercials, but it's great. But you can use them for like those VVT quadrant dampers. Anyway, now one thing about this, if you take these stops off, it's a floating point, right? So you can actually, this will just keep rotating forever. If you apply, voltage in one direction, it'll just, if you take those clips off. So you might want to use it. I don't know if you want to use it for your barbecue, but you put a heat shield on it, you might be able to do that.
Sits on it. I had to sit on it. Yeah, see, you almost had it.
Oh, shit.
Well, guys, we're doing really good on time, so I appreciate you guys would bear with me. I think we might get out of here before 8 o'clock. So let's just keep chugging here. Okay. So now we're going to talk about actuator mounting and wiring. I'm going to show you some pictures of different scenarios of mounting, and then what we'll do is we'll go through the lab, like with the wiring of the different actuators, and then we'll call it a night because that'll be basically the air side. Okay. So here's some examples of wiring, basically of mounting scenarios for actuators. If you notice, if you guys remember us back in the Stone Age, these are our older actuators. These are all that sort of interesting old line drawings, hand-drawn drawings. So the one up here, this one's probably the standard one, right? Direct coupled right to the shaft. We all know that, right? Here's that. What's this thing?
Anti-rotation.
It's that anti-rotation bracket, right? That keeps the actuator rotating. Okay. Direct coupled there. So direct coupled with linkages, I call that direct indirect, right? Because we have one direct coupled actuator on this damper, and then this damper is indirectly coupled through a crank arm and a push rod. Remote mounted is where you fix the rotation of the actuator either on the wall or on the deck of the air handler, and then you have a crank arm and a push rod assembly that actually, this happens to be a jack shaft, right? Jack shaft, and then connect there. Now, how many of you guys have seen this?
dual mounting, right? Two actuators on the same shaft. Okay. There's actually a bracket. You guys probably know this if you've done it. There's a bracket here called a ZG102 that allows you to do that. Allows you actually to stack those on the same shaft. Here's the anti-rotation bracket, and I want to mention something pretty important here. If this has never happened to you, I hope it never does, but I want to mention something here. Every actuator we have has this slot, right? And it's for the anti-rotation bracket to keep the actuator from rotating if it's on directly coupled to the shaft. If you are direct coupling to a shaft or to a jack shaft, one end is fixed by the shaft, right? You put the clamp down, it's fixed. The other end is fixed by this, right? Right? When you mount that rotation bracket, and this is important, don't ever bottom out that pin. Make sure it has room to move up and down, because if you bottom that pin out, you will reef on the gearing inside that actuator, and you will break the gearing, potentially break the gearing. We had a catastrophic situation out in eastern Washington where we had an air handling unit manufacturer. We had an air handling manufacturer that misdimensioned those pins. They bottomed out every one, and they started breaking actuators all over the place. I walked in the air handling unit. In 30 seconds, I said, I know what your problem is. The pin is misdimensioned. Now, if you're foot mounting, right? If you're securing that thing to the deck, right? Or if you want to do remote mounted, absolutely it needs to be fixed. It cannot move. But if it's on a shaft, it actually needs to be able to move up and down slightly. So that's an important thing. I don't know if you guys have ever done this before, but you actually can. If the shaft that comes out of the damper is not long enough to get through the actuator, you can reverse it, right, and put the clamp on the other side. You know, it's got to have enough shaft for the clamp, but you can flip it and you can put it on the other side. You're going to need a nut driver or something, right, or some sort of impact wrench to get to happen, but you can do it. This is just showing you that torque doesn't care, right? Torque doesn't care what orientation it's in, so you can mount these things in any orientation if it's an air damper, right? Actuator. How about for water? No. Any kind of actuator on a valve has to be above the horizontal plane, right? It can be in this plane here. You never mount an actuator on a valve below 0 degrees horizontal. Okay. This is just this is actually something that we make in Europe. This is actually a differential pressure controller. You know, it actually will sense the pressure and do it, but it's just showing you that you can mount these rotation brackets on the side of the duct, and you probably want to put some pookie on this, make sure it doesn't leak. This jack shaft mounting, I actually showed you this, right? So we know what this looks like. Again, this is the jack shaft linkage adapter. This actually saves you a lot of time. What happens is this mounts on the jack shaft. The L bracket that comes with it, there's a tang on the back that goes in there, and then you just bolt this to the bearing of the jack shaft. It takes about 20 minutes or less to do, as opposed to doing the alternative, right, which would be pulling off the jack shaft. It was an idea that nobody really wanted. At the time we came up with it, it was an idea that nobody had asked for, but it turned out to be a good idea. So, all right, here's one of the more important parts of this presentation. We talk about multiple actuator mounting. So what I'm talking about here is mounting actuators on the same shaft or mechanically linked in some way. So you guys know what I'm talking about, right? There could be two separate dampers that are linked by a crank arm and a push rod assembly. You guys ever seen that? You might be able to see, yeah. Or two damper actuators on the same shaft like this. Okay. What we recommend, and this is, I would say it's recent now, it's probably been for at least 9 or 10 years. If you're mounting multiple actuators on the same shaft, or if they're mechanically coupled, we recommend that you use the MFT actuators. So these are those fancy programmable actuators. And the reason why we do that is the AFs, the EFs, and the GKs, which are the ones that you can double up or triple up. They have an algorithm called this piggyback algorithm. The Swiss don't know our language very well. I don't know why the hell they use that term, but it's called piggyback. And what it means is the actuators get paired together and they drive together. Because you guys probably know mechanically, if you gave that one actuator the signal, say you give them both the same signal, say they're parallel wired, right? You give that both actuators a signal, one might start to drive, and the other one might start to drive like 50 milliseconds later or 25 milliseconds later. Well, that's fine, except that keeps happening. They'll end up fighting. They'll get out of sync. So the piggyback algorithm, what it does is you got a master actuator and you got a slave actuator. The master sets the drive time of the slave. So basically, they're both driving at the same time. So we found this out the hard way because for years we did parallel wiring, and what we were finding was, yeah, they'd work fine for like 5 or 6 years, and then they'd start fighting each other, and one would fail. So we said, well, that's not right. So we came up with this way to synchronize the drive. So the way it works is, you start out here. You don't put two NFs together because two NFs equals one AF, so you don't put two NFs in the same shaft. With the AF, you can put up to 3 of them mechanically coupled on a given mechanically linked, and then if you're going to use 2 AFs, you use. We don't have as much problem with the line voltage stuff, so we don't recommend MFT for that. You can actually use just a regular old 2-position actuator here. Same thing with the EFP. Now, you guys probably realize 3 EFs is a big ass damper, right? That's a huge damper. Yeah, and they actually have some of these in data centers. Believe it or not, we actually have dampers where we use 3 EFs, they're huge. So again, same thing. 3 EFs, MFTs on one mechanically coupled, or in this case, we're using 2 EF MFTs for 2-position. And then the GKs, electronic failsafe, we can put 2 of those together. If you ever have any questions on this, like I said, I'm going to give you guys my card. If you ever have any questions, if you're doing new installation on what works and what doesn't, please call me. So this is just, now, here's what I mean by mechanically coupled, but not on the same shaft, right? You got 2 of them on this jack shaft, you got 1 of them on this jack shaft, and then there's a mechanical linkage with the push rod and the crank. Oh, I'm not going to go through these. These are just different. They're sort of cool drawings. You're just showing different ways to pick up the crank arms. I would say, in my own experience, if you can possibly make these parallel, this is the way to do it. This is the preferred way to link up crank arms. This one's a little bit more fun, and I don't know. I mean, I haven't had as much good luck with this, but it does work. All right. So let's go to the lab. Have some fun. So let's see how we got here. 2, 4, 10, 52, 23. Well, we might have to triple up here, but we'll get it to work. They just throw them on the front there. Just before I hand these out, you guys probably know if you have things for it. This is not swag. So this is not swag, so I need these back. I think what we're probably gonna have to do is triple up. So if you guys want to get in groups of 3, then we can do it that way.
This is the.
That's always got Tom, so when they're gone, they're gone.
Just get that to the table there. We'll just see what the
You guys, anybody got a Leatherman or a pair of dice or something like that? You guys just want to turn around back? You guys want to get together?
Anybody else? There you go.
All right, got them out as many as we have.
No, we need some attention.
Yes, sir. Hey, Trace Company else here? All right. I'm not going to sell these. Oh, yeah, that's right. So you guys a group here?
You can double plus.
All right. You guys need 1, 3. You guys are group here?
You can plug into a plug as well.
Here, I go.
Plug in.
Extended.
Wanted it, one gave it to
How's Brandon doing that? Where's
you. Well, I think it's down in Phoenix.
It's hot down there, I can tell you that.
Let's put this strip in the. You guys need a cord down there?
Yeah, we're not letting OSHA into the room, guys, just so that you know. We're not gonna let OSHA, they knock on the door, we're not gonna let them into the room. You guys, group of 4 or group of 2? You guys are 2, you guys All right, guys, does everybody have an actuator and a PS100? We all have power? You guys all hooked up? Yo. Hey, guys. You guys want to get out of here early, right? Okay, good. So does everybody have power to the PS100?
Yes.
Everybody has a LMB 24-3, right? Actuator?
Yes.
All right. So let's start out here. So we're going to start out with the basic stuff. So the first thing I want you guys to do is take the red and the black wire for the LMB 24-3, put them on the post in the lower left-hand corner of the PS100, just the black and the red posts. And what I want you to do is make sure that the actuator switch in the upper right is on the 1 position. You have 2 positions, a 0 and a 1. Make sure it's in the 1 position. You can use your screwdriver for that. So if you hook it up to power, you guys all hooked up? Yeah. Okay. So which way, if you hook up just the red and the black wire, leave the white wire off, which way is the actuator rotating? It's slow. Should be clockwise. If it's counterclockwise, you get the switch in the wrong position. Yep. So it should be going it should be going clockwise. Okay. So it's going, everybody agrees it's going clockwise? Okay. Switch the switch to the 0 position and see what happens. No, not there, on the actuator. Yeah. So now it's going counterclockwise, right? All right. So here's the key to that thing. Guys? Hey, guys? Can you hang with me here for another half hour? Thanks. All right. So here's the thing with that direction control switch. If you don't already know this, that's a really cool tool, and you can check out the actuator that way. But you must know, when you come up to that actuator for the first time, take a picture or something. Make sure you know where that thing is, because if you leave it in the wrong position, you're now out of control, right? So you need to absolutely know where that thing is before you start working on it. Don't leave it any worse than it is before. Okay, switch it back to 1. So now we're going clockwise again. You can use your clutch to adjust the rotation if you get into the stops. Take the white wire and short it to the red wire at the terminal. Just go copper to copper, red to white. Leave it in the terminal block, but just go copper to copper with the red wire and see what happens. It should reverse rotation, right? It should reverse rotation. Okay, so here's what's going on there. Look up on the screen here. You got red, white is 1 and 2. You got number 3 wire, which is the white wire, which should typically go to terminal 3. What you're essentially doing is, when you short that red wire to white wire with the motor, you're actually, when that white wire hits there, it actually reverses the voltage applied to the bridge in the motor, and it reverses the rotation of the motor. So what you do in actuality, if you guys are wiring this, you would put your digital output in series with that white wire. And that's how you would get to position control. When the switch is open, when this switch is open and the switch is in the 1 position, the actuator goes clockwise. When you close that switch, the actuator goes counterclockwise. Does that make sense? So that's your relay. Your digital output relay is in series with the white wire, and that's how you get to position control with 1 digital output. Man, that direction control switch is cool, but it's dangerous. So that's, you guys probably know this when you're in service. Nobody ever sets up stuff the same way. Ideally, everything should be the same, but it's not, right? People are busy. Everybody's got a phone now, pretty much. I just recommend taking a picture of that actuator before you work on it. Make sure you know the way that you found it, just in case.
So you want us to hook the white wire up to the red wire, you're saying, every time we hook them up?
No. What I'm saying is that was to show you that when you apply, when these are shorted together,
right,
that it's the same as closing that switch or opening that switch.
Oh, okay.
I mean, we don't have a relay to do this, right? So we're just showing you that. That's how you can actually get it to happen. In actuality, what you do is wire your relay in series with the white wire. That's what you do, and that's the way it actually happens. Okay. Now, if you want to troubleshoot it, you can do it that way, right? If you want to take your relay out, that's a way to confirm that the thing's operating properly. All right, so let's go on to the next one. On, off. Now we're going to go to floating point. Okay, so guys, hang on, guys. We get out of here by 7:30. Okay? I know it's been a long day. It's been a long day for me, too. All right, so here's what we're doing. Here's what we're doing schematically, but here's what we're actually doing with this tester. We've got black hooked up to common. Red now, you actually have a switch here, and you can either apply 24 volts from 1 to 2, or you can apply 24 volts from 1 to 3. Or, if this switch is in null, nothing's applied. So that's your 3-point floating, right? Either going one way, you're going to go the other way, or you're going to be at null. So here's how you hook it up on the tester. You can go to the other side of the PS100 and hook up the wires on that side.
Yeah, backwards.
So now what you guys can do is just add some switch. Yeah, see, this is based with the switch in the 1 position.
Okay, guys. So if I wanted to do things already wired,
And then just reverse that.
so really the difference on that doesn't really matter. It's more the position of the system. Because they can have that, those controls guys, they get crazy.
You can set them up either way.
long as you keep it the same way. People can switch it, but yeah. That's why I see that direction control switch. Going around with it, make sure it goes back the way it was.
We did a bunch of stuff about it in the Gates Foundation. We were finding where they had VAV boxes.
I was just thinking about that.
Chilled water, and well, you just put hot water on board, and they were 100% you go out there to their little Belimos, and you have, sure enough, it's pretty. And we were finding these switches from back. So you'd switch the switch,
Now you
and
know
the
why
water would open up.
Now why, that's right, that's why you gotta teach the drum, right? Make sure you understand it, huh? Well, most of them. We have some that don't, the cheaper ones, but all of our standard Belimo actuators have the direction sensors now.
And I say AV because that's what it used to be, wasn't it? It was like an AV switch. Was that Belimo?
Yeah,
Or was it all-
0, 1, 2, forget what it says, just look at the rotation. That, to me, that's the minimum. Yeah, that's just.
Yeah.
This thing is a floating point, all it is switch the direction.
Yeah.
Portion determines the minimum voltage signal.
Or that air south or whatever.
This all making sense to you guys? So that the thing with that direction control switch is that now if you do floating point, if you flip that to 0, then that flips, right? Now counterclockwise is clockwise and so it's important when you set it up. Now a lot of people what they'll do is they'll use a Sharpie and they'll define the position they set it up in, right? So again, you can play with that switch, but make sure it's in the right position when you use it. So, unless somebody flipped it before you got there, you know, I mean that's all. All right, so anybody got any questions on floating point? Does it all make sense to you guys? Is this making sense to you? Yeah. All right. So here's one more. We got one more thing to go here, guys. All right. So let's go. Now we're going to talk about. Hey, Tom.
Thanks. Something up for a guy.
All right, thanks, no problem. So, well, we're almost done here, guys. I'm excited. We're going to get done by 7:30, so I'm excited. All right, so now we're going to talk about normal and fail. So these are important things when we talk about damper, well, even for that matter, valve setups. These two concepts get confused by people that have been in the industry many years. So I'm going to try to nail this thing down for you guys that haven't got it before. So we got two different, what we call setups or configurations. We're just going to talk about damper actuators for right now, or damper sets. We got this thing called the normal position. Now you've heard that term before when it applies to relays, but it's not exactly the same as a relay. Okay, I just want to say that right up front. A normal position for a damper system, or a valve for that matter, is under normal operating conditions, if you remove the control signal. Now what I'm talking about there is a proportional control signal, like a 2 to 10 volt signal. If you remove the control signal, the actuator will drive to either what we call an NO or an NC. So it'd be normally open or normally closed. This has to do with control. The normal position is associated with the control signal. The other setup is fail, right? So fail position, assuming you have a fail-safe actuator, we got two different types of fail-safe actuators, right? We got spring return, and we got electronic fail-safe. So let's just talk about spring return. Spring return actuation, if you remove the power, the spring goes what? Fail open or fail closed. Now the open and the closed refer to the damper, right? They actually refer to the damper, not to the actuator. They refer to the damper. So this one's associated with control, and this one's associated with power, right? Okay, two different concepts. Okay, let's just see if we got this thing. So here's the first question. We got an LF24SR. So it's a spring return proportional actuator. The setup is the 2 volt position represents fully closed. The 10 volt position represents fully open. And the whole damper system set up for fail open configuration. All right, that's the setup. So if you lose the control signal on this setup, and the actuator's half open, which way does it go? So you got open, closed, remains in current position. I don't know. Okay, we got some disagreement here. We got taste grade and less filling here. So, all right. So how many for 1? A or A? I'm sorry, A. A. Sorry, I'm getting tired. How many for A? So we got about 1, 2, 3, about 7 or 8 for A. How many for B? Got 1, 2, not as many. Okay, 2 for B. How many for C? Nobody for C, and the rest of you guys are D. Okay, the rest of you guys are D. I don't know, right? Okay. Okay, so here's how the reasoning goes. So let's go back here. What's the word? Power or control? Control, right? Control is the operative word. So control is associated with which setup? Normal or fail? Normal, right. Okay, so now the question is, what's the normal position of that actuation system?
We're going to go to 0 volts.
If you take power away from there, there's nothing.
Not power, control.
So in other words, it's 0 volts DC. So it's not going to move anywhere. It's going to be in.
No, it will move.
No, it'll move closed.
You guys got it right. If you ask the question another way, what happens if you remove the control signal from the actuator, right?
Yeah.
You see 0 volts on the command, right? So where is it going to go? Wherever that 2 volt position is, right? Because remember, 2 volts could be fully open, right? It doesn't have to be closed. It could be 2 volts open and 10 volts closed, right? So in this case, 2 volts is a fully closed position. So when you remove that control signal, the actuator sees 0 volts on the command, and the answer is B.
See 0 volts on the third wire, not on the.
Right, yeah, you still have power, right?
Yeah.
The thing is, the actuator still has power, 24 volts, it just doesn't have a command signal. And so the answer is B. Does everybody get that? Because that's really important.
Yep.
That's really important. Okay, so now, second question is, we got the same actuator set up the same way, and now the question is, we lose the power, and the actuator's half open. Now what happens?
Fails open.
It's A, right? Does everybody see what I'm talking about here? It's A. Because it's fail open. We lose the power, actuator goes open. Okay? That's the distinct. So that's the fail position. Okay. Okay, third question. And now we have LMB 24SR, which is non-spring, proportional. Set up, 2 volts fully closed, 10 volts fully open. We lose the control signal, actuator's half open. What does it do? You get the same 4 choices.
No, it's going to go closed.
No, it's control signal.
All right, so let's just vote here. I hear the discussion. So, how many for A? Nobody for A. How many for B? 1, 2, 3, 4, 5, 6, about 9, 10, about half. How many for C? 1, 2, 3, 4, and then the rest are D. All right, so same question. Okay, so now we have non-spring return, right? So it's non-fail-safe. However, what's the word here? Power or control? Control, right. Control is associated with normal or fail? Normal. What's the normal position? Correct. So it hasn't changed, right? 2 volts is still closed, 10 volts is still open. Now, if you answer C, you're confusing power with control. And it's very easy to do. You have to be very clear. Am I talking about the control signal? Or am I talking about the power applied to the actuator? It's 2 separate things. And believe me, there's a guy in town here. He's been in the business 35 years. He still does not have this down. And it's a little bit amazing to me that he hasn't quite figured it out yet. So anyway, so that's number 3. And then what's that? He sells a bunch of actuators. He sells a lot of them, actually. Yeah. But if you tell him what the normal and fail is, he gets confused. I don't know actually how it works. Anyway, so exercise number 4, we aim to please here. LMB 24SR set up the same way. We have the power is lost. Now what happens?
C.
Right. No power, cannot move. So this is also called fail in place, right? If you guys have ever seen drawings, sometimes you'll see FIP, sometimes you'll see what they call last. And what that means is last position. That's all it means. It means it fails in last position. Now we have a GKB 24 SR. Now it's electronic failsafe. 2 volts is fully closed, 10 volts is fully open. Failsafe position is 40%. We lose the control signal, the actuator's half open. What does it do? Oh, it's 50%. Yeah, it's 50% open.
It's got to go to B.
Actually, so if you lose the control signal, though, it goes zero.
Goes closed. Goes closed, right? Because it's not
Doesn't fail closed, it drives closed. That's a distinction, right? It doesn't fail closed, it drives closed. See what I mean? It's not failing, it's going to its normal position. So the answer is B. You guys, most of you guys got it right. It's B. Does everybody see why it's B? Because there's the 2 volt position, right? So you lose the actuator control signal, it sees 0 volts, it drives to wherever that position, whatever that happens to be. Okay. All right. And then finally, same actuator set up the same way. We lose the power. Now what does it do? It's D, right? It's going to go wherever you set it to, which would be 40% open in this case. Or 40%. That's the 40% of the range. So to summarize, the electronic failsafe, the normal position doesn't change, right? It does what all the other ones do. It goes to normally open or normally closed. But for fail, it goes wherever you set that position. Okay. All right. So let's go back and we'll have hand me you put those back in the box. We'll give you the spring return actuators, and then we'll do the last exercise, and we'll be done.
Yeah, you just plug this one with So if you want too much power off, they can plug something. Yeah.
That's where you want to stay.
Three or 4.
Because it's just signal. Usually
Hey, so guys, look on the screen here. We're going to go back. Just look back here, and we'll show you. What I'll do is we'll just to save the time. What I want you guys to do is to wire them up this way. So you got black, red, white, and green on these 4 posts right here. Now, hey guys, okay. You can adjust the command signal with this knob right here, and then you can read in this window. You can either read your command signal or you can read your feedback signal because you're going to have both hooked up. And I'll go around and just see how you guys are working with that. Okay, just wire them up this way and. Now what you got? Bring it on volts here. So now you got 2 volts right there. So I just changed the command signal there. And then here's where it's going, right? So now what's happening here? So that says normally clock. That means it's 2 volts is here, right? It's 10 volts is here. So you go to that.
this kind of shaft. Yep, you're looking at.
You're looking at the edge of that. Yeah, you're looking at that. The shear rotation.
Because you don't know. Yeah, let's say this is what you're dampering. And this thing so it'll just do all
now you got this yeah, it's going to drive all the way here, right? You see, you get 2 volts in here, 10 volts in here, 6 volts in here.
that way. And you can see the arrow. It's just
But you do your
I've never seen her. You just have to remember that, maybe it's a different direction.
Two different things, right? Remember, control signal, right now.
Because I was hungry. It's been no problems for I got 9 kids. I got 9 kids. Right? Usually it's feedback, right? It's a percentage of this damper. Right? There usually is a percentage. You need some reference. 2 is 0. 100 is 100. Yeah, you don't really, even in control, you don't see a lot of 0 to 10 because you usually need a reference point of 0. This thing doesn't know that it's like, I got 2, then you got 4, then you got 4, what we do is basically the controls guys. So you're saying 2 to 10, so it's like 2, 4, 6. It'll stroke to 0. Percentage of where it is. Like I said, if these get loose, and now
So if
you're
you-
percentage of where this actually none of the shaft, because that's what you do. You go to the unit, you go to the small computer, and you're going to by volts, optimize the players 80 degrees when I'm calling.
Actually,
And you go up there and it's because the shaft is no longer. Usually and that's what he was saying. This little arrow or whatever you're saying, how the direction of the way the straight. So like on a fire, you would always say, okay, I'm gonna put this thing on there this way, and that's with it fully open, my dampers are open, and I'm gonna screech it. Right, when it loses back in the end, right? Because that's how it shoots, right? When it loses back. And so if you do it the wrong way and you kill power, say you shut it right through the actuator, it still stays on. Nice to see that. I can feel it. Yeah, we're not that way. And I do say, you know, we had it so like we just have a couple of you're using this. You're using this for one phase.
So yeah, so as your output.
And there was.
I don't see anything. Right on the sheet. That's why and then what you do is get this on your shaft, slide it up there, but like you were saying, you don't want to bottom down. You want it would just go like that. Exactly. But you don't want it to bottom out.
Did you guys Oh, right. Yeah, didn't know this. No. Well, see what happens on that. Sometimes you're like he's switching when it's switching. What it does, it goes to the rear, it goes back and tags up on the whatever that is. So what'll happen is the feedback goes through it stays there until it tags up, and then once it tags up, it'll slide out to where it's going. It actually has to be resident. That's amazing. So that's the first time it happened here. That's pretty cool. I've never seen that. On one side, they got a match. As long as you're not the camera, they're not well, you still gotta have a private. Well, because it's 95 it's 31. It has 31. Alright, guys, see you Thursday.
Where are these going?
Just up front here, to the left. Left. My left.
Left. Yeah.
Left, right. Oh, it's business.
I don't know. I never knew what that was.
That's Kylie like.
Right? Yeah, they look pretty good here. Jeez.
I'm not supposed to say this, but she calls me to panic every word for her.
See you later.
She's like, she says that.
Yeah, there you go.
And then so-and-so was apart, and then